So now, how do we use this, or how do we apply this? Well, we can use this equation to calculate either delta E or delta H. So let's look at an example. The standard energy change in joules for this reaction, calcium oxide reacting with hydrochloric acid to make calcium chloride in water, delta H0 is negative 217.1 kilojoules. So now, when we look at this, we have to remember a few things from Chem 111. First of all, what does this little subscript mean? This little, or superscript, this little superscript 0, what does that mean? That little superscript is giving you some important information. Anybody remember what that means? It means standard thermodynamic conditions. And what are standard thermodynamic conditions? 0 atmospheric pressure? 1 atmosphere, right? 1 atmosphere pressure and 25 degrees Celsius. And it's exactly 25 and exactly 1 atmosphere, so we can string on a bunch of zeros on our atmosphere. And then because all of our calculations, we use the Kelvin temperature, not the Celsius, this is 298.15 Kelvin. So that little superscript 0 is very important because when it's written down, it is giving us additional information. It's giving us information telling us what the pressure is in the system, and it's telling us what the temperature is. So we look at this equation and we say, okay, I have this chemistry going on, and I know that delta H0 is equal to delta E0 plus delta N sub G times RT. Now, what is delta N sub G? Well, N is the number of moles of gas, and so N sub G represents the change in the moles of gas. For us in chemistry, change is always final minus initial. So delta N sub G is equal to the number of moles of gas on the product side minus the number of moles of gas on the reactant side. So we have to look at our balanced equation and say, okay, these subscripts are important to us now. This is a solid, and the HCl is gas. It's not in liquid. It's not in water. It's not hydrochloric acid. So I have 2 moles of gas on the reactant side. Over here on the product side, I have 1 mole of gas. So delta N sub G is equal to 1 mole of gas minus 2 moles of gas is equal to negative 1 moles of gas. Now, you do not follow your natural inclination to take the absolute value and always work with positive numbers. A lot of people just feel like, oh, we can forget the sign. You can't. So now we have the delta N sub G. We know R because it's a constant. We know the temperature because we have the superscript 0, which means it's 298.15. So now we can plug this in. In Chem 111, you were introduced to a lot of different R values. Which one is the most appropriate to use if we're finding enthalpies and energies? The 8.314 joules per mole Kelvin, because we typically have units of joules, right? Not liter atmosphere. Could we use liter atmosphere? Sure, but then you'd have to do a unit switch. So I think it's easier to use this one. So my delta H0, negative 217.1 kilojoules, is equal to delta E0, what I'm trying to figure out, plus delta N sub G, negative 1 mole of gas, times R. Now, I have a little problem here because R has units of joules per mole Kelvin, and I have kilojoules over here. So I need to get these in the same unit at some time. This is how I do it. 8.314 times 10 to the negative third kilojoules per mole Kelvin. So I just switch it to kilojoules right now and then use that when I'm multiplying out, times 298.15 Kelvin. So negative 217.1 kilojoules is equal to delta E0 minus 2.479 kilojoules, because my moles cancel and my Kelvin temperature cancels. So negative 217.1 kilojoules minus a negative 2.479 kilojoules is equal to delta E0, and that is equal to negative 214.6 kilojoules. So calculating either the standard enthalpy change or the standard energy change is pretty straightforward if you know the other one. If you know one and you know the equation, you can solve for the other. So go ahead and try this next one.